So we're here to talk about OpenWSN. We are users of OpenWSN, the Open Wireless Sensor Network. This website, openwsn.org. If you take one thing away from this, it's to go to that website with all the documentation, links to code base, piles of stuff. The project has been around for decades, it feels like it. Sort of really kicked off somewhere around 2009 with the goal of making a really high-density, high-quality wireless sensor network that didn't exist. And to this day, I think, this is the best wireless sensor network stack that you can get. So it's an open source, right? The Open Wireless Sensor Network, it's a mesh networking system. It's a complete network stack. You flash firmware onto some of the hardware that we have over here, for example. Takes care of everything, routes packets, and delivers them to your application at the end. The reliability bits were things that were super important to bake in back when it was being started back at Berkeley. It's been ported to dozens of microcontrollers. It runs on lots of real-time operating systems as well. And with a caveat you see down here, it's got an ancient code base. It started, as I said, 2009, 2010 era. It still runs Python 2.7. It's had lots and lots of contributors over the years. The code base is this sprawling thing, but it does work. It does eventually work. And as I mentioned earlier, Natalie and I are users, and this is sort of my public service announcement about this code base that I think everyone should use in lieu of the other standards, typical wireless devices, wireless standards that you may be more familiar with. So we're going to switch immediately to a different computer to see what it looks like. I want to give everyone kind of a mental model to refer to so that if you decide to, say, go to the website, dive into this, and try to implement this, you kind of know what to expect, what this looks like. And we'll get, okay, there's a blinking cursor up there at the top. I'm going to turn it over to Natalie to explain what you're seeing, what you're doing, because she's been working with this day in and day out for about a year now.
Hello, again, my name is Natalie, and I'm going to show you what OpenWSN looks like. In this case, it starts with an OpenMote-B board, just one of many boards that are that support OpenWSN, and it's firmware, which you can download and modify from GitHub. I'll just plug this in here.
Plug it in.
Sorry, plugging it in, and
Actually, it might be. Can we realize you can't see it? There we go. So it's connected through one of these dongles. All right.
okay. And if I check my device ports really quick.
All right, that was it. SCONS command.
Okay. All right, and if I flash the board with all the necessary apps and modules depending on the project, just like that, it's ready to connect with other motes and go through the same process, to create a network. And
That was from source. Basically, an alternative take on make.
now, in order to see the actual network, we can use something called Open Visualizer, which helps see the network. In this case, in the top right-hand corner, I have, this is a pre-existing network that's going on in the lab over at the university. I have a couple more modes just like this, connected to each other and communicating some data that I pre-programmed. And you can see there's a root node in there and some other external nodes that are sending or transmitting data to my root node and into the PC so that I can see them here. And then in this terminal down here, it's just showing the web server activity, also OpenWSN, which you can see here, localhost 808, and I have a little toggle which I can choose which of the two nodes that I have in a network right now and assign that node to be a root node or otherwise. And right now, in terms of routing, again, I can see the network. I have two nodes connected to each other. I've done at least 5 nodes to make the picture a little bigger, but or in terms of limitations of ports, I just have 2 right now. Simplified for demonstration purposes here. And even further, we can also plot the data. You can imagine in programming these motes, I can implement applications that look for sensor data. In this case, it's just a number. But then we can plot and visualize the data this way as well. So that's what it looks like working together.
So I can give you a brief tour real quick through some of these windows. So if you can leave it up as is, I'll move the mouse around a little bit. So the one up here maybe looks familiar from a few minutes ago. That's flashing the firmware. Then the one down here, that's just the web browser supporting the web page that you just saw that gives a GUI representation of how the network's organized and its current statistics. The graph here is an MQTT stream that happens to be hosted in Paris for whatever reason. Our collaborators set one up, and that's just sort of the one we've stuck with. But the process running the web browser is also publishing all the sensor data to MQTT. And this last one up here, that's a raw dump of everything going on in the network. So you could have a mesh of 1,000 nodes. They're all going to multi-hop their way back to some root device that pipes things out to the internet. And that root, this is all the traffic that root device is seeing. The web browser, the website is really just a fancy way of scraping all that stuff and organizing it and presenting it in a simpler way. So you've got to run a server daemon, a client daemon. You've got to flash every once in a while, and you've got to plot somehow. But once you get all that stuff up and running, it's pretty stable and self-sufficient. And this is all, again, in my lab. We're remote desktoping into a network that is running live back there. All right, let's switch back over. Huge relief that it worked every time. So I'm going to spend our remaining 10 minutes of this 20-minute slot trying to give you some background of what's going on under the hood. What makes this mesh network unique? Where did it come from? What is it composed of? This is the paper that the chief architects published about it back in 2012. So this would be a good academic start to learning about what is going on, how this network was built from scratch. So this is sort of the one that kicked all this off, right? You see from the title, standards-based, low-power wireless environment. And again, fully open source, so you can sort of do whatever you want with it as compared to off-the-shelf modules, which work great, but don't expose a lot of reconfigurability if you are, for example, a wireless sensor network researcher and want to play around with how the network is organized and how it's built. it is a complete stack. And you may not be familiar with the concept of a network stack, but you're certainly familiar with TCP/IP, which is an example. Oh, yeah, right. I have to point from down here now instead of the usual projector that's up here. So these are two examples of network stacks that maybe you've heard of. There's the OSI model, which is just a model way of describing the kind of nominally 7 things that a network stack needs to do to get all the way from the physical layer, the representation of bits in voltage or light or acoustic signals or wireless power, all the way up to the application layer that we're quite familiar with. And stuff needs to happen all the way up and down. When the OpenWSN project was launched, there wasn't a lot of network stack stuff available that was as reliable as the team wanted. And so each layer over the years has been standardized, finally culminating in, there we go, this one, 6-tish, the time synchronized channel hopping. That was the big one. Trying a kind of different way of reorganizing how you arbitrate this shared airspace that we usually think about the 2.4 gigahertz ISM band, something between 2.4 and 2.5 gig. There's a lot going on between Wi-Fi, Bluetooth, and everything else. Even if you are in a network composed entirely of OpenWSN nodes, you need to play nicely, because again, the goal of this is both low power, density, reliability. You want to be able to support thousands of devices. The commercial version of this, this standard from Analog Devices, the manual that I've got says it supports over 50,000 nodes. And that stuff has been deployed in sites where they have successfully routed 1 trillion packets with 100% delivery rate. Latency isn't guaranteed. There's always the risk of retransmissions. There is always the risk of interference. But they make sure the data actually gets there in the end. So I said time-scheduled channel hopping, time-slotted channel hopping, TSCH is the name of the game here. And this is a representation of what the network is doing. After, say you have this fictitious network with A through HIJ down there at the bottom, way at the end, and you've got these gray lines that represent the wireless links that are possible in the network. For whatever reason, obstacles, interference, those are the links that are available. What the root is doing is hearing each of those nodes join and assigning it a transmission and reception slot. It's assigning it a spot in time on the horizontal axis and in frequency on the vertical axis. So on the vertical axis, you got 16 channel offsets. If you're familiar with the Zigbee PHY, it's the same physical layer that OpenWSN is built off of. It slices the 2.4 gig ISM band into 16 5 megahertz channels. Very helpfully, the standard numbers them starting from 11 instead of 1, but that's a fun thing you can get into, you can discover later. So there's 11 through 26. Anyway, there are 16 possible channels in the 2.4 gig ISM band, and then you've got some number of time slots. And this grid is the schedule at time offset N and channel whatever. You know this link has exclusive use of the shared frequency resource because all of these devices can hear all the other ones. They're in such high density that if they didn't arbitrate, they would stomp all over each other. So this is how you end up approaching 100% channel capacity. You schedule really tightly. You schedule a whole bunch of links in here. You leave some number available for retransmissions, and you've got your network. So this whole thing sends over and over and over again. You can tell maybe from here, we've got 31 time slots here lasting 310 milliseconds, so that's 10 millisecond data exchange slots. So this is an example of one. And then eventually you populate a whole bunch of other nodes in here. Now we've got them all color-coded. And there's some features that you can kind of proactively put into the network, if you so choose, in order to increase bandwidth or to decrease latency. So for bandwidth, we've got 3 slots of the same color. And that means that link, let's see if this, oh, no, there we go. Well, anyway, I'll point over here. Analog method. This link right here with the thicker arrow, that gets 3 packets that it can send every schedule instead of just 1. So now it's got triple the bandwidth of all the other links per go round. When it comes to latency, that's the dashed line over here. Now we've preferentially lined up this link, and this link to be one right after another. So a new piece of data from node F is going to get delivered to the root at A, one node after another. It's going to get there in 30 milliseconds instead of 330 times 3, because it would have to go through the whole schedule 3 times in order to eventually filter all the way up. And so, as we say here in this second bullet, this is a tunable trade-off between all this and energy consumption. And at the lowest limit, on the energy side, if you just have one pair of links, so here node D has a link that will let it send something up to B, and a link that will let it receive something from F. All right? So in that scenario, using this wireless SoC and doing this whole thing every 3.3 seconds, we can expect a 4-year lifetime on a single AA battery. That's if the network, the only thing the device was doing is communication. So if you need a sample from a high current sensor, then this is going to go off the rails. If your sleep mode on the chip that you're using happens to be broken and you can only get an LPM1 instead of LPM3, all right, that's going to put a big dent in your overall battery lifetime. But if the only thing that's pulling charge out of your battery is the radio, your battery, one AA battery in this case, is going to last 4 years. It goes up from there. And to give you a little more insight into what is going on in those slots, this is a diagram of what's happening in about 10 milliseconds. So we've got some preparatory activity right here. We've got the actual packet transmission happens right here. The receiver needs to turn on a little earlier. It's called guard time. So it needs to turn on. There's always the risk of clock skew. Everybody is timing based. Everyone has agreed at the next time index, whatever, we're both going to turn on transmitter, receiver, we're going to exchange data, and then shut off. That's how you save just a gob of power, as compared to Wi-Fi, which just leaves the receiver on 24/7. So the receiver has to power on a little bit early. You get the packet through. The typical packet length for this standard is about 4 milliseconds. That gives you 2 to the 7 bytes of payload. That's a little bit of a misnomer because you usually have to pay some penalty for IP, UDP overhead. But at its most, you get 2 to the 7 bytes. And then the key, one of the big keys to reliability is an acknowledgement. You always have to have an ACK at the end where the transmitter and receiver swap roles. They just say, yep, got it. And then you know that you as the transmitter can delete it from your queue, and next slot, you can send the next piece of data. Otherwise, who knows where the data is? There's no guarantee it's going to get delivered. This sort of handoff, this acknowledgement is super critical, maybe surprising no one. This is a plot from 2009, back when all this was getting started and needed some motivation for 12 million packets exchanged over all of these 16 poorly numbered channels. You got a kind of widely varying percentage between kind of close to 90% packet delivery down to 70-ish% packet delivery. Not as huge of a range as I would have expected. I would have expected Wi-Fi to just clobber and you get almost no data through. And I would have expected that between these big Wi-Fi slots, you get much better performance. You would get closer to 100%, but it's really only 90. In an indoor cluttered high-density environment, the likelihood of you getting a successful transmission is pretty bad. You always have got to have a handoff to the next node and a handoff that confirms it got all the way to the end. Here's this same set of data over time. Instead, this is over a month. You can't see the gray bars on this projector, but trust me, they're here. You can maybe kind of pick out, there's a really faint gray bar right here. Those are the weekends. And so the higher, for any given channel here, If the line is high, if you're looking at a logic analyzer, that'd be a 1. If the line's high, lots of packets got through. If it's low, not very many packets got through. So on the weekends, things work pretty well, and on the weekdays, when everyone's around in the building using lots of Wi-Fi, you don't get a whole lot of packet delivery. But this just speaks to how important it is to have this handoff function at the very lowest level, making sure link 1 to link 2, that works, and then the rest of the network stack handles everything else. It's just IP6 on the way out. So that comes to the last of the prepared slides. Like any good professor, I could go on for several hours about this stuff. There's just an incredible amount of detail that's out there on the website. So this website forwards to an Atlassian page that has been slowly growing over many, many years. That somewhere in there is a link to the GitHub repository with all the code. There are tons of forks in our repository and other people's repositories as people check out this code and sort of make their own modifications. It supports lots of boards, but right now, this NRF 52840 dev kit's $50. It works pretty well with OpenWSN right now. That's the easier one. The OpenMote-B that we're using right now, I love. It speaks really well to my experimental chips, but there seems to be a bit of a run on production at the moment. These NRF dev kits, you can get zillions of them anytime. So that comes to, we're only 2 minutes over. Well done, everyone. Thanks. I suppose we could do some semblance of Q&A. Is that how it works? What do we need? Yeah, okay. I'm getting a nod from the folks who are organized. So maybe a couple of questions if there are any. Otherwise, we'll hang out for a little bit up here as well. Yeah, go ahead. We want to hand this off. I guess this is maybe easier.
Yeah, I think you mentioned a root node or like a special node that assigns channels and timings. I was wondering, is that something that's configured on the device, or is there a self-organizing thing to the network where if that root node gets disconnected, things still keep going?
Right. Yeah. The value of the root node, the risk of the root node is a great question. So when you pull up that GUI we had earlier that showed the 2 nodes connected, you have the option, there's a assign as root node button. So you just tell it, okay, maybe I've got a couple dozen that are connected to a specific, oh, there we go, Natalie's going to pull it up. So maybe you've got a couple that are connected to the computer, and the rest are way out there, not connected. And so you assign that one, and after you assign it, it starts taking over the role of organizing the network. It sends out a beacon and says, look, I'm the root node, connect to me, and then the network kind of forms itself over the course of maybe a minute as everything gets itself straight. Now, if that one gets disconnected, that's your connection to the internet. So that one's pretty vital, which is why it always pays to have several root nodes in the network potentially. And you could add redundancy in this mesh too. There doesn't need to be a single point of failure. You absolutely, right, for any sort of real traditional deployment here at an industry, you always have several root nodes that are redundant. They end up with, all the nodes end up with a sort of preferred link, but then over time, they're keeping statistics on how well a given link works, and it falls below a certain threshold. It goes, you know what? I'm going to stop talking to this one. I'm going to switch to my backup plan, and I'm going to route packets that way. So they always want to have a couple of backup routes, and the root node is no exception. Oh yeah, go. Yeah. Just get my steps in. There we go.
Thanks. Would it be possible for a malicious actor to bring in their own hardware that says, "Hey, I'm a root node. I'm a root node. I'm a root node," and take over the network that way?
Yeah. So the malicious actor part is something that has been worked on extensively in the commercial implementation. There's essentially a pre-shared key that the devices need in order to join, and then they get their own custom key from the network. So that's something that has been considered, but is not part of the open source version. Basically, just to keep things simple. As soon as you add an encryption layer, then you have yet another reason why something doesn't work. But yeah, it's a good point. I think you had it.
What's the range?
The range, that's a good point. So we're using off-the-shelf the TI CC2538 microcontroller. That one we got something like 50 meters of range. But if you, that's outdoor, right? Indoor, it's a dice roll. So the range is really dependent on the wireless microcontroller that you decide to use. Some you certainly don't want to blast so much RF power that you're overwhelming the nearby network. You want to use just enough energy to get to the next hop. So one of the features is to back off your transmit power. So there's the max. Some boards will support up to 0 or 3 dBm. Some boards will support plus 14 dBm. Kind of depends on your power budget, I suppose. Yeah, consult the Friese equation, I guess, for the ultimate range. Yeah.
So I want to know if there is support for backscatter networks, which are like the battery-free device networks and stuff.
That would be great to support, right? It's just a network. The goal with this project and with my own research is to have lots of homogeneously distributed nodes, right? I want lots and lots of identical devices that can communicate with each other sort of peer-to-peer. As soon as you change the game there and you start talking about backscatter, now you've got a heterogeneous network. Now you've got some high-power transmitters and receivers somewhere in the network. You could do all sorts of other things. And so at the moment, this doesn't necessarily support backscatter, although I guess packets are packets. So if you can backscatter and hear a 15.4 packet that conforms to the OpenWSN standard, then you're ready to go. But I don't think anyone's actually ported the network to a backscatter device.
Simple question. How many is many nodes?
How many is many nodes? I have collaborators who've demonstrated many hundreds, and I think there is no theoretical limit. It's up to kind of how much RAM the PC has. I think so I mentioned the commercial version having over 50,000, and I think no one's demonstrated more than the high hundreds, just due to these boards are $100 a piece, and at some point you go, all right, I think we've shown that it works. All right, we should wrap up so that we can do a shift change. But thanks everybody.